All right, yeah. So first of all, thanks to the organizers for the invitation and the opportunity, and for Uwe for being pressing that button.
Yeah, just go on. I will join.
All right, so I'm going to start to compete with the previous speaker with also with a picture. So often people ask me, where is the University of Nice? The university has several campuses, and I'm here. I mean, it's roughly over there, where is the campus where I'm physically staying, and I live over there. So that is a 15 minutes ride with a bicycle, so it's not far away. And as you can see, you should visit me. It's a nice place. All right, so I put a collection of results here, and I didn't know what was the intention of this. It has nothing to do with the previous talk, and I guess many of you are going to be very bored with my talk, but let's see how it goes. So my intention is first to talk about myxobacteria. Many of the works I have been doing the last year were intended to understand myxobacteria. That involves some experiments and a lot of simulations and some simple models. And recently, I mean, like something like, I think I started in 2011 to work on heterogeneous media and the same kind of questions, but put in like, well, defects in the space. So I start with the bacteria, and what are you doing? All right. So so there is a very important difference with the myxo and other kind of bacteria like Bacillus subtilis or E. coli. The main difference is that myxo don't swim. What they do is they glide. How they do that? I mean, they have two kind of motility engines. One is called the A motility engine. The A stands for adventurous motility engine, which works with this kind of focal addition points. And the idea is that the cell, what does is anchor this focal addition point to the substrate, and there is a machinery inside the cell that make the cell rotate around these focal addition points that are assembled, and this is assembled as the cell moves forward. And that is why, for example, the cell has this kind of twisted bread shape here. So there is another hypothesis for this amotility engine, and it's that works by secreting a polysaccharide that gets hydrated, expands its volume, and pushes the cell forward. Nowadays, most people believe that it's mainly the focal addition points, but still some people are like using in models and to explain what they observe, this slime secretion of the bacterium. Then the other mechanism is by this type 4 pili, and the idea is that they anchor this pili somewhere, typically on other bacteria, and by retracting the pili, they can move the cell forward. So there is typically they anchor this on other bacteria that they have around, and that is why it's called the S motility engine. The S stands for social. Okay, now how they communicate, there is a diffusing chemical called the A signal. This is used for triggering different stages in the life cycle, but in fact that's not very important for us today, but mainly the one that is important is the C signal. The C signal, what regulates is the reversal frequency of the cell. If the C signal controls the reversal frequency, what is not known in this kind of bacteria is some kind of diffusive chemical that can be used in order to direct the others, in order to indicate a direction, in which direction the cells should migrate. So, that's the main message. I mean, we see kind of collective patterns in this bacteria without having a diffusing chemotactic signal. So If that's the case, that is difficult to explain why they form these clusters. These clusters are polarized with cells that move in a given direction. So the question was how they can do that, how can they form also vortices and some other kind of patterns that I'm going to show you later. And so in order to understand that, people have, they came with different hypotheses that perhaps there is a hidden guiding chemotactic signal, that perhaps is the slime trail that they secrete and so on. I should have said that they also form this pack of cells and these clusters, and they move together because what they do is they hunt other bacteria. So they really need to form this kind of structure. What they do is they once they find some other kind of bacteria, they are going to secrete some enzymes, and they are going to eat the other bacteria they find in their way.
So the C signal was when they actually touch?
Yeah, they need physical contact.
And then that causes them this reverse motion?
That affects, there is a clock inside, so that was one model by Igoshin and Oster. So the idea is that when they exchange this C signal, these clocks move faster, and then what they are going to do is, for example, they are going to reverse. So suppose at the beginning they are reversing every 10 minutes, then they start to exchange C signal, and they are going to do it, for example, every 3 minutes. And if they are starved, the clock also is going to change the frequency. For example, they will stop reversing.
It doesn't matter where they touch relative to which direction it goes.
They have to be sort of frontal collision. On the side, apparently there is, well, you can see them. I don't have any picture, but there is these channels, and the proteins they have on the tips, and they need to have to touch each other at that level. All right, so we came up with a different kind of idea. We asked ourselves what happens if it's just the cell propulsion and the shape of the bacteria responsible of the kind of collective patterns that we observe. And then we changed our question to ask, what would be the kind of collective effect of a collection of cell-propelled rods. So what we did is that was like several years ago. It's a very simple model. What you have is that these cells are going to be rods, self-propelled rods. These rods have a self-propelling force acting along the longest axis of the rod, and that's basically all. The interaction is only to be induced by volume exclusion, and that we model that by using a potential that penalizes overlapping of the particles. And something very important here is that to realize that these equations are written in an overdone situation, meaning we neglect inertia. If you put inertia back, given that this is a conservative potential, what you would have is that they will do like a granular gas, so that they will get scattered and they cannot get aligned. So because we have here self-propulsion and overdone kind of environment, we write the equations in the overdone situation, then this is going to lead to an effective alignment. And we have some noise term and so on.
But can you explain a little bit more the equation for theta? Is it the angle?
Yeah, so you have an equation for the center of mass, and then you have an equation for the orientation of the particle.
So what's the right-hand side?
This is noise. It's white noise, so you can forget that if you want. So that would be without any kind of noise in the system or temperature. Then this U is the potential, and this F is the self-propelling force.
What about the external potential?
No, it's just the potential when they interact. There you have a potential, a force if you want, force and torque whenever there is an overlapping between them. So you have rods, they are moving, they don't see each other to the point that they start to collide. Collision now is a slow process that is going to produce forces and torque. And for example, if they come like that, they will end up pointing in the same direction.
So that potential depends on all the other rods that are nearby.
Yeah, sure. This is a sum of everybody that is.
All other rods involved.
Yeah,
So this potential is defined only on the surface of each.
Yeah, it's a function of the overlapping that you have with whatever neighbor that you have around you. If there is an overlapping, then you will have a contribution. So the potential depends on this A, and A is the overlapping between the particles.
So they need to physically overlap.
Yeah, they need to.
It is not just volume exclusion.
It's a soft core potential.
As if they are soft.
Yeah, if they were soft.
So it's like a V-check model, where they would like to align themselves.
No, it's very different from Big-check model, and we have studied Big-check model also. I mean, the main difference is that here what you have is a physical model of rods. Effectively, you have an alignment. The alignment that you have is not polar, it's nematic. And I'm going to talk about that. So, yeah, you could try to think of this like the Big-check, but the Big-check is polar, meaning polar, the velocities are going to point in this direction, since the potential that we have is a soft core potential, but is related to volume exclusion. The alignment itself of these two gives you a nematic kind of alignment. If I don't put the self-propelling force and I pack all of them, then what I'm going to find is that they will end up parallel to each other, but pointing in different direction because I have the self-propelling force. But if I don't have the self-propelling force, you will have packs of particles like that, like in liquid crystal, right?
So probably it's close to the Gay-Bond model for liquid crystal, for nematic liquid crystal.
Which model?
Gay-Bond.
The
Gay-Bond. It's a few Lennard-Jones particles attached together.
As polar, not nematic.
Yeah, but I wouldn't call the Lennard-Jones, you have a addition if at some point, right? So it depends where you cut it. But here I don't have any kind of addition. So that could be, there is a model for this kind of guys in liquid crystal that is, some people call it the shish kebab model, and you put balls. So that would be equivalent. But there is no Lennard-Jones.
So actually, could you say a little bit about the form of F is just essentially is it just a constant plus A, the overlap, or A squared? In what form does it have?
No, yeah, I should have written that. It's something like we put and we put here a power.
Could you describe it?
So you have, if you want, the compressibility of your particle, and you have the overlapping of this, and this is how much you are going to let them overlap. Right? So if you overlap what you said that is a maximum compressibility, this is going to blow up. The overlapping between any two particles depends on the, I need to know, I'm going to put it like that. I need to know the position of these two guys. So suppose I, X, J. I need to know also the orientation of each of them. So I need to know theta, J, and I need to know
So is it 2D or is it
theta.
3D?
This is 2D. You can generalize it also to 3D, but this is the simulations, and most of the things that we have done is in 2D. So I don't know if, well, it's not very nice, but you understand. So I need to know the position of one of the rods, the center of mass of the other, the orientation of both. Because of the position and the orientation, then what I need to compute is the overlapping, which is here. So what is going to do, the potential is going to penalize that. So it's the resulting motion that I'm going to observe is a motion where that area is going to get reduced with time. I mean, if I let the system relax, I'm not going to have any overlapping.
What data do you use?
In fact, I think we play with different ones. I think the simulations I'm going to show you now is one. But that you can make it like stronger, the kind of repulsion between them. That depends also on the value of A that you put. The simulations I'm showing you are quite soft. Even though they are quite soft, you will not see almost any overlapping.
So one last question on the equations.
Yeah.
So you're saying it's overdamped. So what is the mechanism for dissipation here?
It's the substrate.
The substrate.
I don't have any liquid here. They anchor to the substrate,
the substrate.
and I assume that I mean they move at a relatively constant speed.
And so these factors basically will
Oh
scale.
yeah, this would be the friction coefficient.
No, but it also scales with the geometries. For example, the
Sure.
angular velocity.
Yeah,
will-
this for example is relatively like 1/2 of the value of this one, and then you have this one, and you have
that one's an angular.
Macintosh, for example, that has proposed different kind of friction for a rod, but that if it's in a suppose sort of thin film or things like that, or a line on the
I want to
bottom of
simply comment that those factors are probably geometric, so the angular one is probably essentially a moment of inertia type term.
yeah, it is.
So you have geometry encoded in there.
They have geometry, and you have hello, and you have to decide which kind of I mean coefficient you use, and regarding the geometry, and I mean, given the fact that for bacteria is quite sophisticated a mechanism, I have the impression that these kind of arguments, I'm not that sure whether they apply, because they have the focal addition point. The focal addition point, that means that they are anchored to the substrate. Anyway, we have used something. We look at the paper where people computed that, particularly the paper by Macintosh, where he did some kind of estimates, and we use the estimates he proposed for the simulations I'm showing you now. So this, I have the movie that I can show you, because I know that here there are some people, Hugo in particular, which was looking at this kind of problem. So we did that in 2006, and we can see that the particles end up on the boundary, and there is some interesting effects there. This looks like high density, but it's low density, in fact. I mean, once you see that they go to the walls, you can understand that the density is not that high. So, and you, Tani, have been also playing with that kind of things. Okay, this is an old movie. I can show you later, but I'm going to focus mainly on this. So this is the model we have just discussed. What you can see is that these simple rules lead to local alignment. The local alignment allow you, even though the alignment is nematic, allow you to form a couple of rods that move in the same direction. You can see that the cluster interact between them. Here you are going to see, I think now, that two of them collide and form a larger cluster. You can see also that this larger cluster typically tend to lose particles that are on the boundary, and so you have interesting kind of effects in this simple system that the only thing that has is the self-propulsion and volume exclusion. So how can we understand or characterize the kind of collective effects that we observe here? Well, there are several alternatives. What we have been doing for last year is mainly we have focused on clustering. And clustering, what you can see here is that there is a transition. So what I'm going to explain you now is this is the packing fraction. So think of that as the density or as the packing fraction if you are used to it. And this is the aspect ratio of the rods. So if these rods are either very elongated or the density is very large, you are going to cross this red curve. Later on, I'm going to show you how you can estimate these things. I mean, like how you can calculate this. But once you cross this line, what you are going to see, if you are here, you are going to see that the cluster size distribution, which is this subset here, which in fact, I always say that is the cluster size distribution, but is a weighted cluster size distribution, tells you, well, you see it with a peak and large cluster sizes, that is not longer monotonically decreasing. If you are below, you see an exponential decay, and when you are on top of this red curve, is a power law with an exponential cutoff due to the system size.
So this is shown for a particular velocity of motion f.
This is almost general for whatever you can think of. and I'm going to show you later on. We found that at least in 5 different models, the
So what I
same
mean
kind
is
of dynamics.
If you change the value of the self-propelling force, does it move that line?
If the self-propelling force, it doesn't change.
It's invariant.
It's invariant.
And if you turn the force equal to 0,
Well, yeah, you go to a
is there
singular limit.
Is there a liquid crystal transition?
Yeah, there is a liquid
Where-
crystal
where's
transition.
that? Where's that?
No, here is for a finite
But
velocity.
what I'm asking, the liquid crystal transition is where in this phase diagram? Way in the upper right?
No, you would move to, you move in that direction. So you wouldn't expect, this is very low densities and you still observe the kind of transition. I'm talking anyway not an kind of nematic transition at the Onsager theory.
Because
That's
it's
something
actually, the Onsager theory, if it was an Onsager theory, it would be at about kappa 10 and 8.3, so it would be...
is shift that way, but it's shift considerably that way.
So what's the definition of PC here? Missed that.
P is because we wrote, and that was this theory where this P is a dimensionless parameter, but it's going to, that could be, for example, you can think of that like the density or the aspect ratio of the particle. Then I'm going to show you what is P.
No, I know what PC is.
PC
So what
is the critical value of your
So what is
dimensionless
the
parameter.
signature of criticality?
The power law here, for example.
So the onset.
The onset of having a peak at large cluster sizes. So before that, what you have is an exponential decay in cluster size distribution. What I say, this cluster size distribution anyway is the probability that if you pick up a random particle, that particle belongs to a cluster of mass m, right? So it's not the number of cluster of mass m that you have in the system, which means that there is sometimes some confusion that is the ng if there is the number of cluster of mass j multiplied by t divided by n. This is what I call, well, I should have called everything n probably, and this is pm. So some people call this NM cluster size distribution. I call the cluster size distribution this object. And n is the number of particles in the system.
So, I'm confused. You've got P of m on your y-axis, on the right-hand picture. Right, P of m on the y-axis.
Yeah?
Yeah, and then you say P is equal to PC. Are those the same P's?
No, this is, yeah, alright.
Okay, what are the P's?
This
P
is the critical parameter.
intercept?
One was small p, the other was big P.
Okay.
And the big P is the control parameter. And this control parameter is what I said, once you go to some kind of Smoluchowski theory with fragmentation and so on, that is going to contain the aspect ratio of the particles, the density and so on. So everything goes in that P. Alright, so
You're gonna write that down.
yeah, I'm going to show you the equations for that if we arrive to that part. All right. So conclusion is that for the self-propelled rods and the theory I'm going to show you later, what you can understand that at low density, I'm going to talk mainly about density because it's what we can control with the bacteria, not that much the aspect ratio of the bacteria. So at low density, what we expect is an exponential decay. At the critical density, the power law. At large density, the peak and large cluster sizes, which is this object here. All right, so now when I...
Sorry, the large density behavior, that's somehow a finite size effect, is it?
Wait, this thing...
This peak.
No, it's not a finite size effect. This is because you're having a transition in the system.
But I mean,
So
if I was-
like the gelation that you would get in some of the systems. But it's not a condensate. And I'm going to go to that part later on if I arrive.
Self-tripping.
It's self-driven.
Trap themselves.
Yeah, they trap, I mean, what they do, what happens here is they are forming very large cluster sizes, but they are not going to form one, but they are going to form several of them and move in the same direction. So when we see this, what we are observing is a system formation of large clusters that move in a given direction. So it's not, they are not static. And then you can see the difference when you have one condensate in the system. the intention would be to show you that if I have the time. So, but well, I was planning first to show you what we found with the experiment, which I think is interesting. So what I showed you before is the kind of feature that we expect for the clustering for the self-propelled rods. Now I'm going to show you the experiments with bacteria. So we have playing with 3 different mutants. The wild type does everything that I described you before. The cells reverse, they have the S motility engine, and they have the adventurous motility engine, meaning they have the focal addition points, they have the type 4 pili, and the cells do reverse. Now, these guys are the guys that we studied in more detail. These are the more simple ones. So what they do is they don't reverse. They don't have the type 4 pili, meaning that the adhesivity is not very strong for these mutants. And the only thing that they have is the A motility engine, meaning that they move, in principle, if that would be as the self-propelled rods, straight ahead. And it's basically what we observe also in the experiment. These mutants, here the A plus, S plus, freezing minus, are ones that they do not reverse but have the both motility engines on, meaning that they have the type 4 pili and the focal addition point. So they are a bit sticky compared to this one. All right, so when you put this in the experiment, what you can see is that cells, as we were expecting for the rods, when they collide, they tend to align and go in the same direction, but because it's nematic, if the collisions is in this form, meaning particles coming in opposite direction, they will end up parallel to each other but moving in opposite direction, so anti-parallel to each other. Right? So that depending how you collide, you could end up moving in the same direction or in opposite directions. But that is going to be enough to build some kind of order in the system. Now if you put the cells in the Petri dish and you observe what happens, what you observe here is I don't know if you can see very well, you observe the formation of large clusters. These large clusters are polarized and the cells are migrating in a well-defined direction, which is indicated by these arrows here. All right, so now if we look at the cluster size distribution, that was our favorite quantity here is again misleading this PM. This is clusters that this is the cumulative distribution, what I'm plotting here, and I never changed the slide. So, but this is not PM, but the cumulative. So M being smaller or equal to M is here. All right. So, and what you, the message of this slide, this is for different densities, and for the mutant that we saw here, this is the data that I'm showing you, what you can see is the time evolution of the cluster size distribution, and you can see that after some time, curves seems to overlap.
So
which
we can't read the color scheme, so what's the initial time and what's the final time?
You start around, this is the non-motile, we have a...
The point of the graph's not the cut, not the bar. So what is the initial time, what is the final time? I can't
no,
read that.
this is density,
Yeah.
Time.
and the different colors is time.
Yeah, so what is the question?
So time goes in this direction. So blue, and then the next color, I don't know if it's a green or what, or a different blue. So you see, you go in this direction. So when you see that they overlap, is that you are looking at. So finally, the conclusion is that for an biological experiment, I would say that this is a relatively good indication that what we observe is that steady state cluster size distribution.
So you have eta what on the top there. So
This is the packing fraction.
packing fraction.
Yeah. No.
Semi-log scale.
Yeah. So now what I'm going to show you is that because you find a steady state cluster size distribution, now what you could try to do is to look at the steady state cluster size distribution, a function of this number here, of the density. This is what I'm going to show you in the next slide. This is what you see here. cluster size distribution, this time is not the cumulative, but the cluster size distribution, the definition here in the blackboard. And so then what you can see is for the three mutants that I showed you before, in fact, the first two mutant and the wild type, and what you can see here is that if the density is low, or the packing fraction is low, you get an exponential decay. You keep on increasing the density. At some point, you get something that looks like a power law. And if you keep on increasing the density, at some point, there is a peak at large cluster sizes. That is what you can see here. Now I'm going to show you that something interesting happens when we go to larger densities than what we analyzed initially. That is that they form vortices. That part we still don't understand. Now if you look at the mutants that are more sticky, with the experiment and everything was more difficult to do it, but at least what we can see is that it seems we have very bad data for lower densities, but it seems that it's very close to what we observe for the A+, S-, free C-, for the sticky mutants that do not reverse. So it seems that if they do not reverse, they behave similarly. Now the wild type is very different, as you can see here. If they do reverse, what you can see is that the distribution is roughly exponential for all packing fraction. And what happens at higher density is very different, again, than with the previous two mutants. What we observe is the formation of kind of mesh-like structures. And this is what I'm going to show you here. So this curve for the cluster size distribution corresponds to pictures in the experiment like this one. So you have the clusters, but if you keep on going to higher density, at some point they start to form this structure. This is a vortex, and you see that they start to crawl on top of each other also. So this is not longer a two-dimensional picture of what happens. They go to the third dimension here, so they start to crawl on top of each other. And I didn't put the movie. I think we have one in YouTube, which is very short, but at least still you can see that these plates that you see here, they are like rigid kind of discs that are rotating. We cannot see what is happening inside, really, but what we can see is that they may rotate in different directions. So, for example,
a wedding cake structure we're looking at here
is what you see here. I mean, the problem is that we have very bad imaging, so we cannot know exactly what is going on, but the structure is like this. And you are looking here at the sample. So what we see is that, for example, if this guy moves in that direction, is rotating in that direction, often this one rotates the opposite direction. So now the question is what happens inside, because inside could happen like these guys have been doing, which is that perhaps we have a layer like this and another layer rotating on the other direction. And because we are overlapping them, what we see is just the rings, as you can see here. And so when we look at the rings, we see the rings that not necessarily move all in the same direction, but often they move in opposite direction, meaning clockwise.
One cell thick.
This is each layer is one cell. Yeah. So this kind of cake thing is one layer of cells. All right, so.
How are you able to know that it's one cell thing?
I mean, because it's phase contrast, we more or less look at this and we see each time, you see this halo thing? It's a kind of empirical thing, but we are quite confident that it's like that. You see that, you see like the levels here, 1 step, 2, 3. Now, if you look with the microscope closer, it coincides with your impression. So, well, this is not really very high tech, right? But we look at that carefully, and it seems that it's really one single cell layer each time. I mean, 1, 2, 3, 4, 5 here.
Looks like you're going to use something for all microscope.
Yeah, if you give me one, I do it. But that's a problem. We don't have. But yeah, that will be the. Yeah, well, I mean,
How do you know the direction of motion?
because if, oh yeah, I shouldn't, in my computer, I have it, it's there, and my computer doesn't work, but you can see that they rotate. And there is the same problem that they have, I mean, because we didn't mark the cells, what you see is the fruit, you see clearly them moving. I mean, the disk, they are moving. Ideally, we should have used a confocal microscope, have them labeled, and I hope this is going to come soon, like this kind of experiments. But that, I mean, requires some work and money to do that.
There's a substructure that looks like they're pointing, are the bacteria pointing radially or tangentially?
Oh, here, no, it seems to be, what you can see is a stream that is fusing and getting into the lower kind of disc that we see here, and inside here they are.
But I'm looking at that very top layer of the cake.
The
Look at the
the
image.
top,
The
no,
top layer,
no,
the
no,
second
no.
layer of the cake, it looks like there's a radial.
No, but they are not. They are relatively parallel to each other, like in a disc. They are, yeah, you understood. So,
No, yeah. So they're pointing in a tangential direction.
Could you
Yeah,
show
they are-
top?
Like that, tangential.
yeah, something like that. But again, it's very difficult because of, if you look at this, you cannot. I mean, you need to look at with the microscope and go closer, and then you can convince yourself that it's like that.
And do they always alternate directions?
Not always, but often. Yeah, we don't understand. I'm just showing you what
I
we
think we
found.
should
And
move beyond how much we read into these pictures, because we don't have the experimentalists here perhaps to.
I mean, yeah, the problem is that we did that with a confocal microscope, and then we analyzed these things. I mean, one needs to use better techniques. We still cannot know much. Okay, so anyway, you go to higher density. The thing, this was, we were looking at clustering, and we tried to concentrate just on kind of one layer kind of activity and collective effect, but when we increased the density, we started to observe this, and then we reported about that. I mean, we observed that, we saw that was something interesting, but we still don't know really what is going on here. And the same is this is a bad figure, but anyway, with the wild type, they form this kind of mesh-like structure, and they seem, again, it's difficult without having them labeled, that they are traveling across this kind of high density regions that you see here. So there are cells moving one direction and moving in the opposite direction, and they form this mesh-like structure that, again, we don't know how to explain it and how to model it. So this is kind of food for making some
So it
interesting
looks like
models.
there's only one cluster in this case.
There is a percolation associated to that. I mean, the percolation transition. That's why, before I change it, but what you can see is that when problem is that we have few movies. I mean, this is a problem when you are not really an experimentalist, you know, stupid things. So the clusters typically start to reverse, and you have cells moving in one direction and the other, and they start to get elongated often, these clusters. And at some point you have some others, I mean, some cells are going to migrate, so see, if the density is relatively low, the picture is similar to the one I showed you before, but they tend to get elongated, and at some point these clusters start to connect. And when they connect, it seems that the cells cross from one side to the other, and again, we don't understand. I'm just telling you what we have observed with the confocal microscope. And
So actually, now going back to this cluster size distribution here, you claim that, so this is supposed to be exponential. So
this is exponential.
yeah. So you're not without the big cluster. So you
No.
don't have the big cluster.
Never. You never get the big cluster. Before getting that, you start to see this mesh-like structure.
Yes, but
That is a big
that's
cluster.
big cluster.
That's one cluster.
All right, but I was, yeah, sure.
So
When I was talking before about clusters that move in one given direction. So I add to the cluster not only a bunch of particles that are together, but they are together and moving in one direction. So remember this picture, okay, so you see these are bunch of guys, cells together and moving in one direction. with the wild type, what you start to see is that some of them move in one direction, but because they reverse, this with time they get very elongated. At some point they connect to each
Well, I
other.
guess the point is this is eta 0.38 according to the image.
Yes.
Right.
And the
So what value-
curves on the left are much lower eta.
Yes.
So what
the-
happens
the-
is for higher eta you lose that altogether and you just have one cluster.
Yes, one cluster, one percolated kind of cluster.
And
Yeah.
what value of eta is it that you have that crossover?
We don't know because we should have added more kind of density. We were looking at this and suddenly we got it at 24 already. We were observing some kind of a structure like this one, but the image were not very good, so we got some better kind of analysis for higher density, and then that's we didn't put all of that. So we got some relatively nice curve, only 3 I would say, and then the rest of the values were at the beginning we were just assuming that we did something wrong in the experiment, and so we discarded all that. And at some point that was again and again the same thing, and we said, okay, yes, it's happening something that we don't understand here. Yeah, well. All right, so the conclusion and what I think is very interesting, I mean, that we reported but we don't really understand, is for these chi mutants we observe a higher density deformation of these vortices, the spontaneous formation of these vortices, and for the wild type this mesh-like structure. And as I said before, we observed that, we have seen that is what happened, but we don't have any explanation still, like a solid one for any of these. This kind of a structure seems to be connected with what we observe with self-propelled rods with addition. It seems that they produce something that probably is close to what we observe here. But still, I wouldn't say that that's the answer. All right, so I moved to some other statistic that we did for these two mutants, not for the wild type, and then what you can do is something that I don't know, that a quantity that people found very interesting, that is the number fluctuations. And what you do is you put a box of size L, you count how many cells you have there, you go to a larger box, you count how many you have there, you go to a larger box, and you keep on doing that. Now the average value of this goes like this, very simple. So it is the global density that you have in your system multiplies by the area of the box. But the quantity of interest here is the variance of that of that quantity here. So the variance is this, and that should go with an exponent beta. This is not very difficult to understand and to do the calculation. Now, if this beta is 1/2, this is telling you that the central limit theorem works and the fluctuations are normal. Now, if when this beta gets larger, it's telling you that something different from what you would expect for the central limit theorem, and these are called Geiger fluctuations. So now we played that. I mean, we performed that the statistics with the cells, and what we found is that if you go to very low densities, it seems that fluctuations, these number fluctuations are normal, but as you keep on increasing the density, you go to this kind of apparent Geiger number fluctuations. This Geiger number fluctuation and the transition coincides with the point where I showed you before you get the peak at large cluster sizes. So it seems to be associated with the effect of having very large clusters in the system, which means that it's not exactly the same of the, probably, of the Geiger number fluctuations as Ramaswamy, for instance, defined, right? I mean, this would be connected to clustering, and we cannot assume that the phase is, we have an homogeneous phase. That is what I'm trying to say.
So again, this critical exponent you're pointing out here is at the critical value.
No, this is, as you can see, is for many.
So what is it at the critical value?
0.8, but above is 0.8 also. That's
also, so it persists beyond that.
So yeah, you can see all the curves, they are all collapsed there. And this value 0.8 is the same that we observe for the self-propelled rod simulations. which I don't know if it's a coincidence or what, but I mean it's the same value. Now, I think it's, well, I guess I'm going to finish us with the bacteria. There is the question whether we can assume that the cell propulsion and volume exclusion can be a general mechanism for spatial self-organization in bacteria, and I don't know the answer, unfortunately, but there have been, the group of Sweeney have done similar experiments in 2010, and the definition of cluster is not exactly the same because they kept, they use in the definition also the orientation of these clusters, but they the measurement they did, they obtained basically the same kind of exponent that we measure. For the clustering, they measure 0.85, and what I showed you before, well, I should go really back. So you see the value that we measure, yeah? So they measure 0.85, and they, well, we use here just our theory to check whether we could predict the same things that they were observing in the experiment. We can. But the interesting thing is that they also measure these giant number fluctuations, and with an exponent that also is very close. So what I showed you before was 0.8, here is 0.75. And now the interesting thing is that here we don't have any liquid. With the mutants I show you, that, I mean, we use the focal addition point, that they are migrating on the surface, they collide, they form these clusters and so on. They move very slowly, but the system is very different from Bacillus subtilis. And Bacillus subtilis, they swim in a thin film. They move way faster than ours, and even though they kind of, at the level of the clustering and the statistics that I showed you before, the exponents are very close to each other. So as I put here, this is a sort of a question, but probably that indicates that cell propulsion and volume exclusion, if we believe that here we can neglect hydrodynamical interactions, lead to the same kind of self-organization, spatial self-organization in bacteria. So the main message then is with the gliding bacteria, where you can neglect hydrodynamical interactions, and with the mutants, where you can also neglect biochemical signal regulation. What you can have is formation of polar cluster, the transition to clustering, and which you can use to define what is collective motion in this context, right? Collective motion as the existence of large clusters of cells moving in the same direction. And the comparison with Bacillus subtilis, which I think is interesting. Now, the question is I promised to say something at least about clustering and about the theory. So how can we understand what we observe with the self-propelled rod simulations, and how we can understand what we observe in bacteria? So before doing that, I would say we can slightly change the question and ask ourselves what how can we understand that volume exclusion and self-propulsion are enough to produce so many collective effects? So, and for studying these kind of things, we study a simplified self-propelled rod model, which is a model that you have the particles that move at constant speed, and what they do is they align nematically, right? I mean, they may point in the same direction or in the opposite direction. So this is a la Vic-check, but with a different symmetry. Don't let me skip that. Then you have this.
I mean, could you go back and at least describe the model a little bit so we can? Yeah,
I can do that. But this is getting late. All right. So the model is very simple. What you have is, what we tried to do is we were thinking that what produces all these effects is just that there is an effective alignment mechanism. So So we have our particle with a given velocity, which is going to be fixed, it's constant, the speed, not the direction. It's going to look in the neighborhood what the other particles are doing, and what our particle is going to do here is going to try to measure some average quantity here. It's going to find what is the director, thinking of each of these arrows, not like an arrow, but like a line, sorry. So it's going to compute the average director here. Imagine that you have several ones that move, some of them here, some of them there. So let's assume that is around here. So then our particle is going to be happy. However, if the director points in this direction, this particle will turn and will align.
Rotational alignment and translation.
Yeah, you have rotation, but rotation not with it's not a ferromagnet. What you have here is I mean, if they don't move, is what you would use as a model for probably liquid crystals, static ones. And
is that a type or something is missing in the second equation, like delta t and theta it? You know, the increment of theta. I mean, you should have a previous theta in the right hand
oh
side.
no, you don't, because I work. Even though I don't like this is the kind of Vikshe kind of models. Then that the second part of the talk was with this defined in continuum time, which I prefer, and a proper Langevin equation, but because of historical reason, people were incremental delta t here, but making the alignment instantaneous. Yeah, the Vikshe model is defined like that. So if I move back, that changes anything because you have the same kind of symmetries, but you can write this thing as where I put it. You can write the equation like this. So it's the same. So, but in the Vikshe model, the alignment is instantaneous. There is no relaxation time for the alignment. Anyway, the equation is not a typo. It's defined like this. So, right, this is. So this was the thing. So now, why we use this model? We wanted to figure out whether what that was the alignment, what was responsible of all the effect that we observed. So you can put that in the computer, for instance, and see what happens. What you can see is that you can get the clustering that I showed you before. You can get Geiger number fluctuations with the same exponent that I showed you for the bacteria. And what else? I mean, and you get the formation and low density of these bands, which is quite interesting. So that there is no addition or anything in the model, but these green regions are regions of high density, so you have a very rich collective dynamics. Cells are moving along this line and like going down and up. And this band is very unstable. It's going to do that forever. All right. So so what I said, you get roughly the same kind of clustering as before. So you can do the same. And now, how can you understand this? Okay, what you can do is you can write down Smoluchowski coagulation, Smoluchowski equation with fragmentation. You can assume that the cluster move independently in order to work with the equation. You can assume that clusters do not exhibit a decrease of their mobility with their mass. Once you put this assumption here, you are saying that the model is a non-equilibrium one. Otherwise, they should slow down if the clusters are very big. And the number of particles is conserved, and the cluster dynamics, we have approximate that as a fission kind of process where you have two clusters that if they collide, they will form a larger cluster, and a kind of fragmentation, we simplify it by assuming that there is kind of evaporation, meaning that only particles that are on the boundary and the ones that are able to escape from the cluster. Now, the physics of the problem goes in these reaction rates that often are called kernels, at least in this kind of context. And here what the A is going to depend of the scaling of the scattering cross-section with the mass of the cluster, and this B is going to depend on the scaling of the perimeter with the mass of the cluster. Now you can write down these equations for these objects, that is the number of cluster of mass J at time t. You have a hierarchy of equations. This is for cluster of one particle. You would write something similar for having clusters of 2 particles, J particles, up to n particles. And then you can put all your physics in the collision kernel and fragmentation kernel, and you can build the P, this dimensionless parameter that I showed you at the very beginning. You can try to figure out what happened with do a finite size study of this system, and this is the important point here, is that the thermodynamical limit is with the number of equations going to infinity and P going to 0. Yeah, I finished. And okay, if you do all that, you can describe the kind of curves that I showed you before, and you can even fit them. I mean, that works is relatively general. There is a little thing that I'm just going to show you in this slide. If the exponents associated with the scaling of the scattering cross-section is equivalent to the scaling of the perimeter, then what you have is a genuine phase transition. Otherwise, it is not a genuine phase transition. So the peak and large cluster sizes in that case would be a finite size effect. But if these two are the same, it is a genuine phase transition. All right, so I stop here, otherwise it's going to take forever. Thank you.
Maybe a couple of questions.
So you have alignment in that model, you know, the V tends to align with the average of the neighboring V's, but it doesn't tell you why or how. In other words, you said it doesn't have fluid hydrodynamics in it, but actually part of that mechanism could be hydrodynamic in the context of Bacillus subtilis. So in what sense isn't it hydrodynamic?
In the sense that in Myxobacteria, I think it is not.
Myxobacteria, right.
But that's why I try to compare, because I think like it's puzzling that the exponents are so similar. So I say, perhaps Bacillus subtilis is very different, but if hydrodynamical interactions are not that important, and it's mainly volume exclusion what is leading the process, then you would expect the same kind of exponent, and you get the same kind of exponent, which I think is points towards that hydrodynamical interaction perhaps are not that important in Bacillus subtilis.
Well, they're not that important in determining those.
Drawing it out, they're very dense. That's a very dense. That's why
it's very dense.
You
Yeah.
barely have any fluid there, so you could argue.
Right.
No, it's mostly because there's only a single layer of cells. So
there is only a single layer of cells, and I presume that they may be important, but there is another thing.
I mean, just because for two different systems you get roughly the same exponents,
But it's very roughly.
doesn't mean
It's not exactly.
No, there are experiments.
that aggressive, but it doesn't mean that the mechanisms are identical, and the time course of the development of these of clusters, for example, could be a bit different in different systems.
Absolutely, but that doesn't indicate that they are different, right?
Words,
I mean,
the fact that they align is you're very convincing about, but what it wasn't very convincing about was the mechanism of alignment.
But the alignment, there is a point here. I mean, you can get polar clusters having nematic alignment. So it is not necessary to invoke a polar kind of alignment, which may come from hydrodynamical interaction. It might be there. Bacillus subtilis may be totally driven by hydrodynamical interactions. But if you assume that what you have is nematic kind of interaction, you would have a kind of collective dynamic that looks very similar. So I'm saying it could be the case that this is just volume exclusion and cell propulsion. It's not a statement. I mean, it's not a strong claim. I put in a question mark when in the slide, right? I say it could be the case that it's just volume exclusion and self-propulsion and an enigmatic alignment.
So I was interested in this morphology you showed in the last movie, where you had these thin stripes.
Yeah.
So that looks to me like you could write down an effective law of motion for the stripe. So
In the, you
so
mean?
going to the movie, you showed a movie of collective motion of essentially a stripe moving
Right.
in the plane. So it suggests that you might actually have a law of motion for the stripe.
Yeah, there is
rather emerging.
There is a recent paper by Université and others, which they wrote down a continuum model for that, and then you can
For the free boundary, for the stripe.
not really for the whole thing. So they use kinetic theory and they derive some equations. So noise plays an important role there. But yes, the answer is I think you probably
so
can.
What is the structure of that geometric evolution equation?
No, it was you know the Bertan paper where they.
I'm not in the field.
Well, I can show you then the paper and that they use that kind of approach.
More questions? Well, if not, then let's thank the speaker once again.